Hey everyone, today we're going to be learning a little more about the French mathematician Francois Vieille. Many know him as the father of algebra, but as we've learned throughout the course, this can be a little unfair to the mathematicians that came before him, but it's also a little unfair to Vieille, because his mathematical ideas stretched much farther than simply algebra. So, a little bit about the early life of Francois Vieille. He was born in 1540 in Fontenay-le-Comte, France, and he was a cryptographer. He was actually involved in the French government a lot, and he worked as a cryptographer in the Spanish-French Wars, and he was also an amateur mathematician and astronomer. But his father was a lawyer, and he studied at the University of Poitiers and earned his degree in 1560 in law. But after only 4 years, he learned that law wasn't for him and mathematics was where he wanted to go with his life. So he took on a job supervising the education of Catherine of Parthenay, who is another famous mathematician. He moved to Paris in 1570 and published his first work in 1571. During this time, the French wars of religion were all throughout Europe and decimating France. And Vieille was actually a Huguenot, and he was living in Paris when King Charles IX authorized the massacre of the Huguenots in 1572. So, obviously, he wasn't caught up in it, but it must have affected him during this time of it must have been quite a sequence in his life. But after this, King Charles actually appointed Vieille as counselor of the government of Brittany in 1573, and after King Charles IX died, King Henry III took over, and he appointed Vieille as the Royal Privy Councillor, and he did a lot of work code breaking. He did a lot of cryptography work in this position. He was appointed in 1580, and he was banished by his political enemies, most likely because of the religion wars and because of his religion. His political enemies banished him in 1584, but this actually worked against them because during his banishment, Vieille was able to fully devote all of his thoughts and his thinking to mathematics, and much like Newton did during the Black Plague, Vieille was able to come up with his most significant mathematical ideas, and it was a very prolific time for him. One interesting thing about his code-breaking work, during the French religion wars, King Philip II of Spain was supporting the Holy League in France. The Holy League was opposed to the French government, and he would send coded message to the Holy League, and eventually one of these messages fell into the hands of the soon-to-be King Henry IV. And once he got this letter in his hands, Henry IV sent it right over to Vieille. He was already a prominent mathematician in Europe at this time, well known, and after some time, Vieille was able to decipher the code and sent the fully decoded message to Henry IV, and eventually Philip II discovered that his unbreakable message was broken, and that the French were aware of his coming military plans, and he then complained to the Pope that black magic was being employed against his country, when in reality it was just Francois Villais. So here are Villais' major works that he accomplished throughout his life. His first book in 1571 was the Canon Mathematicus. His next book that came out, and this is his most famous book for sure, it was his algebra book called In Artem Analyticum Isagoge. And lastly, he came out with a couple more books in the 1590s, one of them being the Supplementum Geometriae. First, we'll start with the Canon Mathematicus, his first published work in 1571. This was more of a mathematics as a tool book. It was a mathematical introduction to astronomy. Obviously, astronomy during this time was still huge, with all of the navigation happening in Europe. And this book covered trigonometry. And it provided things like trigonometric tables, which I don't know if you'll be able to see here. It's probably pretty small, but those are some trigonometric tables. And he actually gave the mathematics behind constructing these tables. It also provided details of how to solve both planar and spherical triangles. We'll skip ahead a bit to the Supplementum Geometriae. This book he published in 1593, and he gave solutions to some of the more famous Greek mathematics problems, like doubling the cube and trisecting an angle. He also showed how to construct tangents at any point on the Archimedean spiral. And he was also able to calculate pi to 10 places using a polygon of 6 times 2 to the 16th sides. That is a little crazy. I wonder how long it took him. But another interesting thing that he did in this book was he provided the earliest infinite representation of pi in this type of sequence. He said that pi was equal to 2 times 2 times 2 over the square root of 2 times 2 over the square root of 2 plus the square root of 2, and so on. You can type it in your calculator if you want. It's all there. It's a little crazy how he figured that one out. But next, finally, we'll come to his most famous work, In Artem Analyticum Isagoge. This is the first textbook to ever introduce using letters to represent both known and unknown values. Villais, for example, in this book, he used vowels to represent his unknowns and consonants to represent his constants. So here I have some examples of what his notation would look like compared to our notation. So the expression 3x cubed plus 4y squared, Villais would take a bit different approach. In using his notation, he would come up with 3 times a to the I power plus 4 times e to the I power. Interestingly enough, they hadn't started using the exponent. They hadn't used numbers in the exponents. They simply used the number of i's to denote what power they wanted to go to. So in this case, they used 3 i's to indicate that they wanted to have a times a times a. And a little more about his notation. We have a equation here, and he would he used the plus sign that we use today, but for his subtraction sign, he used our equals sign that we use today, and for his equals sign, he used sort of a long equals sign, kind of a double equals sign. And down here you can see how he used his consonants to represent constants. In this book, VA was also to make a whole slew of improvements to the theory of equations, and this is because using his algebra notation with vowels as variables and constants, consonants denoting constants. Goodness. He was able to make general statements about these equations, and this helped with pattern recognition and figuring out solutions to these equations. Interestingly enough, though, VA was really concerned with homogeneity of dimensions in these equations, and he made his law of homogeneous quantities stated here. The first and permanent law of equalities or proportions, which, because it is conceived from homogeneous quantities, is called the law of homogeneous quantities, is this: homogeneous quantities must be compared with homogeneous quantities. This is most likely due to the fact that when we have an equation such as x cubed equals x plus 1, he saw it as comparing a cube to a line, which didn't really make sense in his head. He thought that you could only compare cubes with cubes and lines with lines. So this thought process really restricted VA to the form a cubed or x cubed plus b squared a plus b squared z, because all three of these terms are in dimension 3, with this one having all three unknown terms, this one having a square constant square coefficient times the variable, and then this last one being that same square times a different constant. And interestingly enough, VA is actually responsible for our use of the word coefficient in math. A little bit about his later life. Henry IV converted to Roman Catholicism because of the French Wars of Religion. This was more of a political move, and it helped him gain the control of Paris. And VA followed the suit of his king and also converted to Roman Catholicism in 1593. VA in the 1590s, after his algebra book, was prominently known in Europe, and Adrian van Roomen, another Dutch mathematician, he proposed a problem solving an equation of degree 45, and the ambassador from the Netherlands told Henry IV that no Frenchman could solve Roomen's problem. So Henry IV, turning to his main man, he gave the problem to VA, hoping that he would be able to solve it. And it took VA some time, 2 years it took him, but he was able to solve it by finding an underlying trigonometric equation. And as a result, he had solved the problem, and Roomen and VA became good friends. VA actually proposed another problem to Riemann, which he used his parabolas to solve, I believe. So, one of the quotes here from VA that I love is, I, who do not profess to be a mathematician, but who, whenever there is leisure, delight in mathematical studies. Because he was never a professional mathematician. Math was always a hobby for him. His job was in the French government, but he really enjoyed math. It's interesting what he might have been able to accomplish if he was a professional mathematician, but I think he enjoyed his time with math as a hobby. And he moved back to his hometown in the early 1600s, and he died shortly after in 1603. And there are my works cited. I hope you enjoyed this presentation about Francois Vier. Hope you learned a lot more, and I hope everyone has a wonderful Thanksgiving, a happy holiday, and good luck to everyone on the final, and I will see you later.